So today's lesson is on free energy, right? So I will tell you in brief. So past few days we were learning about entropy, and in the AS we were learning about enthalpy. So finally, combining entropy and the Gibbs free energy, combining entropy and the uh, enthalpy, we have Gibbs free energy, right? Gibbs free energy. Okay. So Gibbs free energy is a formula made using temperature, entropy, and the enthalpy. Once you plug in the variables into this formula, you can tell whether reaction is thermodynamically feasible, whether the reaction is feasible or not, whether the reaction is happening or not. That's all. It doesn't tell you how fast it is happening, right? It will tell you whether reaction is possible or not. And it is like a horoscope. And when people are, in the our part of the world, they have horoscopes. So they look at the horoscopes and check whether the couples matches or not. Right? If the horoscopes are not matching each other, it means they are not meant to be together. Right? So therefore, there's nothing can be done. It means, yeah, they have to look for something else. Likewise, this is the horoscope. Before we are doing a reaction, we check, right? Before you are doing a reaction, there are two reactants, right? We check just like the horoscopes whether they can react each other or not, whether that marriage is going to be successful or not. Before they are getting married, we look, right? So this is uh, it involves everything, products and reactants. Yes, it makes you check whether two reactants can be reacted, right? So if the two reactants are reacting, it means we have a product, right? That's all. So we have to consider about the reactants and the products both, right? Because sometimes same reactants can give different products. So therefore, it depends on both the reactants, products, and the temperature itself, right? Okay. Very simple value, right? Gives free energy. If you can remember, last time we did a little calculation on system entropy. Remember system entropy, right? So entrophy change within the system. It means between reactants and the products, right? Now Gibbs free energy, I will tell you the equation. Now this is called standard Gibbs free energy, right? At the standard condition. It means under other conditions also we can derive a formula. Delta G naught equals delta H reaction, enthalpy of a reaction. Huh? You are given reactants and the products. Based on the reactants and products, we can calculate delta H, right? Minus now temperature, the reaction has happened, and when the reaction has happened, the amount of change of entropy in the system, right? Delta H system. Very easy, right? This is called the grip. Very good. Temperature by the difference of entropy of the system. Right? Okay. Now remember, what can you tell about the units? What is the unit of Gibbs free energy? Now here we have delta H, right? So it means it should have the same units of delta H. Otherwise, we can't add those subtract now. You must have same units, right? So delta G also what? What are the units of delta H, right? Usually, Gibbs free energy is given in kilojoules. You can write it in joules also, kilojoules per moles. If the delta H given in kilojoules per moles, this one is also kilojoules per moles. If you can remember entropy, what is the unit of entropy? Kilojoules per moles per Kelvin. That is why we had to multiply by Kelvin. So therefore, Kelvin to Kelvin get cancelled off. Okay. See nicely how it is balanced. So you know now the labels are what this is standard enthalpy difference, enthalpy change. This is the standard entropy change of the system. This is the Gibbs free standard Gibbs free energy change. Remember, they all are talking about the change, right? Gibbs free change. When the reaction is happening, how much of Gibbs free change has happened, right? The Gibbs free energy change, standard Gibbs free energy change or difference. That's it. Now I will give you some data. You can do it. I'll give you some questions. After that, actually, we can discuss some thermodynamics questions. Actually, right? Exam questions. Uh, these are the values. Calculate the free energy change. Free energy change means what? Sometimes they will tell you free energy change. Free energy change means Gibbs free. Gibbs, right? They are talking about Gibbs. So always make sure to balance an equation. I'm telling you. Sometimes they may not give you a balanced equation. Always these are given for balanced equations. That's the standard way of doing it. So do not even attempt to do a question without balancing an equation. This is the equation. Check whether it is balanced or not. When for the balanced reaction, for the balanced equation, when this reaction is happening, the enthalpy change has been plus 135 kilojoules per moles. Entropy change has been plus 344 joules per Kelvin per mole. Find the Gibbs free value. Later I will tell you by looking at Gibbs free energy how to tell whether a reaction is feasible or not. Very good question. Now we H no standard means what? Under standard conditions, right? Standard, standard temperature was standard state temperature 290. So you got to make that assumption 298, right? You got to make that assumption because this reaction is happening under standard conditions. G naught value. Find the G naught. 344. It is given in remember joules per Kelvin per mole, right? Here it is given in kilojoules. This is given in joules. Be careful, it must be in the same units. So you will have to do a unit conversion. Yeah, round it off, right? Yes, good. 32.5, right? Just plug in the values, right? You must be getting 32.49 kilojoules per mole. Delta G naught equals delta H naught delta S T, right? So just plug in the values, right? We'll move on to another reaction. They can give you the question in different ways. This is a combustion reaction. C2H5OH plus balance the equation first. I am telling you for a reason. Otherwise, you may get wrong values because we have to find it for the balanced equation, right? So gas. Now you are to find delta G naught. Here for this also you are given a chart. Using this chart, you got to find the substance delta G naught. Here it is given in kilojoules per moles. C2H5OH liquid minus 175 O2 gas 0 CO2 gas minus 394. Yes, delta G for this compound. If you can remember how you found entropy difference, same way you can find. So these are the two ways of questions being asked. What is the value? Minus 448. I don't get that. I'm getting something else. Check it again. I'm getting minus. Uh, okay, so minus 1300. kilojoules. Isn't it not minus 1300? 1300? Check. Okay. Minus 448. I told you use the balance formula here. Did you balance it first? See, I told you. See, now how many are there? Check when you balance it. There must be three oxygens. Then two carbon dioxide are being produced. Three water molecules are being produced. So here you must multiply by what? Three here. Water. Carbon dioxide and two here. Oxygen doesn't make any difference, but still three. Then your values are going to be different, right? For the balanced stoichiometric equation, that is what I told you. That is why I actually didn't balance it for you. Yeah. Okay. Minus 1300. Right. Let's move on to reaction feasibility. Now with these values, how to decide? It's very easy, right? By looking at these Gibbs free value, how to check whether it is feasible or not. Reaction feasibility. So you just need to know these things. Once you calculate the delta G value, if the delta G naught value is less than 0, reaction is feasible. Reaction is feasible. Thermodynamically possible. But it doesn't tell you how fast it is going to happen, right? That is a different thing. Kinetic factor. You can only tell they can get married, but when are they going to get married, we can't tell. There are such things no, in the horoscope. They say okay, they are matching each other, right? They are a good couple, but yes, that is only if reaction is feasible. Reaction is possible. It can happen, but how fast or how long it will take, we can't tell. Reaction is feasible, or you can tell spontaneous. But in other terms, you can tell spontaneous. Reaction is spontaneously happen. That is all. But how fast, how long it will take, we can't tell. That is something else. And the kinetics, we are learning that. If delta G is positive, not feasible. Greater the delta G value negatively, reaction is highly feasible. More positive the delta G value is, reaction is not possible. Thermodynamically, right? Not kinetically. Thermodynamically means spontaneously. That is all. Think like that. Thermodynamically means feasibility means it's a thermodynamic factor. It comes under thermodynamics. So just see that the reaction is spontaneously happening. That's it. Right? It can happen at any time. It's under standard condition. It can happen. If you put the reactors together, it is happening. Definitely, it is happening. But we can't tell how fast it is going to happen. Right? It is react. That's what I'm going to tell you when they are like a horoscope, right? They match each other, but we can't decide. Yeah, when they are going to. Yes, less than zero. Negative. Negative gives you. It can happen. It is happening actually. It can happen. It is happening. It is happening. Delta G is positive. It is not happening. Huh? These are theoretical figures, right? So based on the theoretical figures, we, for example, if there are two reactors, if the delta G values are negative, under the given conditions, if you put them together, reaction is happening. That is the only thing we can tell, right? These are theoretical values, right? Experimental values may differ because the conditions are different, and the kinetics also coming into play. I told you how fast it is happening. We can't tell this by looking at this. Keep that in mind. We can't. It doesn't tell you how fast. That is what I took that analogy. They are getting married definitely, but we can't tell you when they are going to get married. Sooner or later, we don't know. Something like this. That here also, right? If the delta G is zero, what can you tell? Still, the reaction is feasible in some syllabuses. We tell the reaction is feasible, right? But yes, if delta G is zero, still it is feasible. But here we tell it is borderline. Borderline. At least delta G must be zero for a reaction to be spontaneous. At least, at least delta G must be zero. At least delta G naught must be zero. You can't be lower than this. Low means if it becomes positive, it is an issue, right? Up to zero, possible, right? So feasibility and spontaneous it's similar actually, right? Not the same, but it's similar. Similar, not the same. Similar. It gives the same meaning. Yes, yes, it is automatically happening. Spontaneousness. If the reaction is visible, reaction is spontaneous. If the reaction is not feasible, reaction is not spontaneous. Okay. If the reaction is visible, it is spontaneous. If the reaction is not feasible, it is not spontaneous. Got the point? Now I will give you a chart. Now you can, without doing any calculation, you can predict uh, whether the reaction is possible by looking at the positiveness and negativeness of the other variables in the equation. Right? I will give you a chart. Let's see whether you can fill it up. Now, when you are filling it up, you can plug in random values to this formula and tell. This is the formula delta G is delta H naught minus T into delta S naught. Randomly plug in values and try to get an answer. Without plugging those, you can tell manually. Delta G, right. Uh, the reaction spontaneousness, whether it is spontaneous or not, feasible or not. So that is all you should tell. Now I will give you the for first one I will do for you. If delta H is negative, delta S is also is positive. What can you tell about delta G? If delta H is negative, if delta S is positive, what can you tell about delta G? Always negative, right? Why it is positive? Both these variables are negative, right? T is anyways absolute temperature, it is positive. So therefore, multiplication of this is become negative. So therefore, always negative. So it is always what? Negative. Always feasible. Other things I will let you figure it out. I will give you fill in the blanks. Positive, negative, 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 positive, positive. Let's see. Uh, if delta H is, if this one is positive, delta H is positive, right? Delta S is negative, 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 positive, negative, negative, positive, no? Always positive. So always think of the formula. Never feasible. So they are asking these in MCQs, right? So in that case, just do not memorize it. Remember the chart, right? All never, never, always not feasible, right? Think and answer. Think. It depends on the temperature, right? So let's say at low temperature and high temperature. So when both are negative, it depends on the temperature. High temperature, low. Here also low and high. Then find the. Okay, feasible. I'll put a correct mark. At high temperature, not feasible. Right? So we can tell only at low temperature. Delta H is possible. Delta H at low temperature, uh, not feasible. At high temperature, only at high temperature. So don't memorize these things. Just think of the equation and find only at high temperature. Okay, right. And actually, we can summarize this. Right? We can tell now delta H is negative means what? Reaction is endothermic or exothermic. Delta H, if it is delta H is negative, what can you tell? Whether it is endothermic. If delta H is negative and delta S is positive, for example, endothermic reaction with the system entropy is also increasing. System entropy is increasing and it is an endothermic reaction, right? Then the reaction is feasible. This you can write at another column, right? It is exothermic. So exothermic reactions, when the system entropy is increasing, reaction is very feasible, right? Endothermic reactions means when the energy is released, system entropy is increasing, it's very feasible, right? Now, exothermic reaction, when the system entropy is also, you have to consider both. I told you, no, just because it is exothermic, we can't tell actually. We have to think of the system entropy also, right? So that is what scientists were so curious about it. Just because it is exothermic, still we can't tell. We have to think of the entropy also, right? Only by looking at the entropy we can comment. Right? And if the reaction is here, endothermic. End. Let's talk about here is also endo. In endothermic reactions, if the system entropy is also increasing, reaction is Uh, Feasibility depends on the temperature. See, it depends on the temperature. Right? Here it is what? Again, exothermic. In an endothermic reaction, in an endothermic reaction, yeah, write it down. It's important. They are asking like that, no? They are asking if the reaction is endothermic, and sometimes they may not even tell you. They will let you decide with the enthalpy values, and they will ask you whether the reaction is feasible or not. Right? So they will ask from that way also questions, right? So endothermic reactions, when the entropy is decreasing in endothermic reactions, when the entropy is decreasing, always the reaction is not feasible. Right? In exothermic reactions, when the entropy is negative, it depends on the temperature. Right? At high temperature, not feasible. At low temperature, it is feasible. In exothermic reactions, in endothermic reactions, when the entropy is increasing, at high temperature it is feasible, low temperature not feasible. Right. Okay. So this tells you why again, by looking at the enthalpy only, we cannot decide on the feasibility. Right? Delta is always come into play, but in some cases even temperature matters. In first two scenarios, temperature does not matter, but the last two, temperature matters. That's a summary. Uh, right. I will give you a question. Let's see whether you can do this. It's easy, right? Determine whether its reaction is thermodynamically feasible or not. Whether the reaction is spontaneous or not. question. Calculate the Gibbs. Tell whether it is thermodynamically feasible or not. Calcium again. Balance the equation all the time. With oxygen gas, you get calcium oxide solid. Delta H is given minus 635.5 kilojoules per mole. And coffees are given for calcium solid 41.0 joules per Kelvin per mole. Delta H naught oxygen gas 205.0 joules Kelvin per mole. S naught calcium oxide solid 40.00 joules per Kelvin per mole. Using this data, tell whether the reaction is thermodynamically feasible or not. So once you plug in the value, you must be getting delta G naught. First calculate the delta G naught for the balanced equation 573.8 kilojoules per mole. Since it is less than 0, it is actually a highly feasible reaction. Very feasible. Remember now, since we are changing the temperature, now these values are not values, right? These are just delta G. Why? The temperature is changing now, right? Since the temperature is not standard, right? So this must be not non-standard. Keep that in mind. Then only we can think of the cell, right? These are not standard values. Why the temperature is changing? Right. Another one. Right. I will give you a question and let's see. In this way also they can ask you a question. At what temperature? Temperature. The reaction of aluminium oxide. Aluminium oxide with carbon become spontaneous. Be very wisely answer this, right? This is another way of they can ask you questions based on Gibbs theory. They may ask you whether the reaction is feasible or not, and also in this way also they can ask always balance the equation or check whether it is balanced properly. For this reaction, enthalpy change is plus 1336 kilojoules per mole, and coffee change plus 581 joules per Kelvin per mole. Find at what temperature it becomes spontaneous. Or uh, the minimum temperature it becomes spontaneous. How do you find that? How do you find? I will give you this. Very good, very good, very good, very good point. Right? Any reaction starts to become spontaneous when G becomes zero, not G no, G becomes zero, delta G becomes zero. Reaction starts. Very good. He has very good. So when you plug in the values, delta G should be zero. So zero equals delta H into T into delta S. Right. So you make the T subject. H value is given as what? 13336 and S is 581. So it is starting to become one. Yeah, it is what a kilojoules, right? So therefore, very good observation. So it should be 2299 Kelvin. Right now, look at it. Now it is at it is starting to become spontaneous. Delta is positive. Yes, delta is positive. Uh, so therefore, it is a highly um, endothermic reactions, right? No, not an high. You can't take that with delta H is I think endothermic reaction. So therefore, it is becoming spontaneous. What? Um, only at high temperatures, right? At low temperatures, what will happen? This will not be spontaneous. So this is the minimum temperature you need, right? If you look at the chart, when delta H is positive, when the delta S is positive, Only at very high temperatures reactions are becoming spontaneous. Right? So therefore, you are finding the minimum temperature. At least this temperature is needed. So in that way also they can ask you question. Uh, right. There's one more thing. I will give you the for homework. Right. Uh, Graphing of this equation. Graphing of Gibbs equation. Now I want you to um, plot a graph, right, using the Gibbs equation. How delta G naught will change with temperature. Temperature when enthalpy and the entropy remains constant. Right? Enthalpy and entropy remain constant. Can you find that? You can do it quite easily, right? It's just mathematics. If delta G is in y-axis, temperature is in x-axis. Now you have to think of enthalpy and entropy also. These are constant values. Yes, constant. So how this may look like? You can assume it's an endothermic reaction with positive delta S. Right? Endothermic reaction and the entropy change in the system is positive. Delta is positive. It's like curvature, right? No, no. I think you know this. First of all, you write the equation. Delta G naught equals delta H naught. Right. So I told you these are the variables. So I will make it y variable, and this one is what? Temperature is the x variable. Right. Temperature is x variable, and these are constant values. Delta is what? Endothermic. So therefore, positive m, right? Minus mx delta H C, right? Now, if let's say if this is a spontaneous reaction, right? If it is a spontaneous reaction, delta G is what? Minus 1, right? So we can convert into what? Plus y multiplied by y minus c plus mx. So therefore, how would the graph be look like for endothermic reaction? Negative, something like this. Delta G, here temperature could look like this. But remember now, this graph is only for uh, endothermic reactions. Now here it's an exothermic reaction. C is minus 2. This is now it has become C minus, right? So it must be what? Exothermic reaction. Exothermic reaction with positive delta S system. Right? Finally, that is how. That is why. Then only you can derive this. Yes. Yeah. Endothermic reaction is positive delta S. So these reactions are always what? Uh, Endothermic. Right. Yes. Hmm. Okay. So that's all for today, right? And with this, we are done with the Gibbs free energy, and we can move on to kinetics. Right? Okay. Take care. Bye bye.